Hey everyone, welcome back to the channel. Today we are diving into an exciting real-world NLP project, which is fine-tuning a transformer model for emotion classification using Hugging Face ecosystem. By the end of this video, you will know how to load and explore a real-world dataset of tweets, pre-process and tokenize text using DistilBERT model, fine-tuning a model with emotional label, evaluate, interpret, and publish your model to the Hugging Face Hub. If you are new to Hugging Face Hub, or you want a hands-on project to practice your NLP skills, this video will be the one for you. So let's jump in. First things first, this cell installs our core libraries like Dataset for loading and pre-processing data, Hugging Face Hub for publishing models, and FSpec for file systems and access across platform. Most packages were already installed, but Dataset and FSpec were upgraded. So there were some pip dependencies warnings about version mismatch, but you can ignore these unless they throw errors during training. Great. Now we will use the Dataset library, which is a powerful and flexible tool for accessing, inspecting, and pre-processing datasets directly from the Hugging Face Hub. We will load the emotion dataset using the function called load dataset. This dataset contains short English text samples, tweets labeled with one of 6 emotions like joy, anger, or sadness. And remember that we have 6 labels for this dataset. The dataset contains 3 splits: train, validation, and test. Each example in this dataset is a tweet labeled with one of 6 basic emotions. The label field is an integer index mapped to emotions name. This is where we load our data. From dataset, we import the load dataset function, and we call this load dataset function passing the name of our dataset, storing it into an emotion dataset. Let's load this dataset and print its type and the dataset itself. So let's load it together. As we can see, it's a dataset dictionary that has 3 splits: train, validation, and test. The train dataset contains 16,000 rows. Each row has the text of the tweet and its label. The validation dataset is 2,000 rows, and the test dataset has 2,000 samples. So we get the 3 splits: train, validation, and test, and each with text and label columns. So let's extract the training set from the full dataset dictionary and print a few things about it to explore it. So we say, take the emotion dataset, take only the training dataset or split, and store it into a training data. Here we extract the training set from the full dataset. To do so, we call the emotion dataset and specifying only the train split, storing it into the emotion dataset. Okay, now let's inspect what we just loaded, and specifically the train split. So to load the train split and extract it from the dataset, we will call the dataset, specifying that we need only to extract the train split and storing it into a variable called emotion train set. And then we will print the train set number of rows, we will print the column names, and we will print the features for the dataset. So let's run this cell. Now it tells me that your emotion train set contains 16,000 rows. Each one has the text and label columns, and the size of the training set is 16,000. These are the column names, and these are the column features. And if we go, we will find that the label has a class label that has all the 6 emotions for each tweets in our dataset: sadness, joy, love, anger, fear, and surprise. So there are 16,000 training samples, and labels are mapped to 6 emotional categories. And that's what we will train the model to recognize and predict for new tweets. So let's speak at the first example. Let's print the emotion train set at index 0. And we can see that the first row in this training dataset has a text called "I did not feel humiliated," and this is a label 0, which means this is a sadness emotion. Let's run it. Let's now sample 5 tweets so you can see what our model will be learning from. So we print the emotion train set starting from index 0 until index 5, and I need only the text. And these are real human expressions with informal tone and emotional buried inside. That's why fine-tuning a model here is so powerful. And we can see here the first tweet, second tweet, starting from I can go from feeling so hopeless to damned hopeful till the end, until the end of these 5 tweets. Now, what about the labels for these tweets? To print the labels, I'll do the same. Print emotion train set, the first 5 rows, and they want the label column. So let's run it. So this gives us the raw input the model will learn from after transformations. We will see this in the following cells, and let's go step by step. Now let's view the first 5 tweets. This gives us a better sense of how expressive and messy natural text can be. If we look at the first tweet, it says, I did not feel humiliated. And the second one, I can go from feeling so hopeless until the end of all the 5 tweets. As you can see, tweets are short, informal, and emotionally rich. Perfect for our model. Now to print the labels, I will print the emotions train set and bring me the first 5 rows, but I need only the labels columns. So we can see that these tweets are labeled as 0, which belongs to class sadness, and 3, which is class anger, and 2, which is class love, and again, another tweet that belongs to anger. This numeric encoding will later be used in loss calculations during our training process. So remember that these raw labels will be converted into a tensor values that the model can use. Each number represents an emotion, which will map back to labels during our evaluation process. Okay, that's great. Now, before feeding our tweets into a transformer, we must tokenize them, turning words into IDs. Transformers like BERT and DistilBERT use subword tokenization, which offers good coverage of rare words, smaller vocabularies, and efficient training. We will use Hugging Face Auto-Tokenizer class, which is a smart wrapper that loads the correct tokenizer for our model. So to do so, we will import the Auto-Tokenizer class from our Transformers library, the DistilBERT tokenizer as well. We can set the pre-trained model checkpoint to our DistilBERT based uncased model, and this will be considered our model checkpoint. To load the tokenizer for this model, we will call auto-tokenizer from pre-trained, and we will specify this model checkpoint, okay? And we'll store this as tokenizer. Now, let's print some information about this tokenizer, like what's the vocabulary size for this tokenizer, what is the maximum model length, what are all the special IDs, what are the special tokens, and what is the model input names. Let's see what is the output of these print statements. Great. Now the tokenizer vocabulary size is over 30,000 tokens, and the maximum input length is 512, and these are the IDs of the special token IDs. And if you want to learn more, you can view one of the previous videos that I will share with you at the end of this video. And then we have these special token names, which are unknown, separator, padding, CLS for classification, and the mask. And the model inputs are the input IDs and attention mask. So this is what we are doing. We load the tokenizer for the DistilBERT base uncased. Then we inspect the configuration like vocabulary size, context window size, spatial tokens, and model inputs. And these outputs are essentials. For example, the bad token is used to align the sequences in batches. The CLS is used for classification tasks, and that's the hidden state that we will use for final predictions. And the input IDs, along with their attention masks, are required inputs for most Hugging Face models. Now let's tokenize a sample sentence. For example, assume that we have this sentence. This tutorial will show you how Hugging Face models can be fine-tuned using transformers and PyTorch. And I'm storing this into a text, and I'm passing this text variable or this text string to the tokenizer, and I will receive it as the encoded text. And let's print the encoded text. So it will print that these are the input IDs, and you can see that this is the CLS, the 101 special token, and for each word or subword I will have its token ID and the attention mask at the end. So we tokenized this sample sentence to explore how Hugging Face transforms raw text into something a transformer model can use. So we get a dictionary with two main keys: the input IDs, which is the IDs for each token, and the attention mask, which means which tokens to pay attention to with value 1 or to ignore with value 0. And the structure that you see is exactly what a transformer expects. The input IDs include all the special tokens like CLS at the beginning and SAP at the end. So this gives us a peek into how the sentence is chunked and structured before entering the model. Now let's visualize the tokens so we can map numbers back to actual words. Let's now print the tokenizer, convert IDs to tokens, and pass this encoded text, which includes these IDs, and print them back to their own text. As we can see, these are the tokens that we have from this text. So the 101 is the CLS token. Then we have this. Tutorial has been split into tutor and IA. This helps the model to recognize unknown or rare word. And this is how we can convert those token IDs back into readable tokens. This is helpful for debugging, understanding how your model sees text. Okay, now let's decode the tokens back into a string just to verify that the full round trip process is complete. So to do so, we call the function that is called decode, and we pass this encoded text input IDs and receive the output into a decoded text. To print this decoded text, we'll find this text string with special tokens, and we can see that this tutorial token is back into one word. So this confirms that the tokenizer can reverse the process, which is useful for debugging model outputs. Okay, now that we understand how tokenization works for one sentence, let's scale it up, which means that we need to tokenize the whole dataset using the Hugging Face maps function. So first, let's reset the format of the emotion dataset. Now we define a simple tokenization function to apply to every batch in our dataset. So we define a function called tokenize batch that takes a batch of dataset and pass the text column to this tokenizer and returns the results with padding equal true and truncation equal true. So we run this function. Now we need to use it. So we will try it on a small batch of our data set. So for the first 4 rows in the training split of the emotion dataset, we print the original text of these 4 emotions, and then we pass this batch of 4 rows to the tokenized batch and print the results. So let's run it. And as you can see here, this is the output. We have the original batch or the original text batch. This is the first I did not feel humiliated, and we can see that it applies the tokenization for the first row, the second row, and third row. And as you can see here, that the first row has been padded according to the maximum length of this batch. So now this batch is ready to be fed into a BERT style model. Now that we know that our function works fine, let's now tokenize the entire dataset using the map function with batched equal true, which allows efficient parallel processing across the dataset entries. So let's run this cell. So instead of routing manually, we'll use the Hugging Face powerful map function, which applies the tokenization to the entire dataset fast and in parallel. So we call the emotion dataset map, and we pass the name of our tokenization function, which is called tokenize batch, with batched equal true and batch size equal none. Take care that this line applies the tokenization function to all splits. training split, validation split, and test split using the patched equal true. Now we get input IDs, attention masks, columns added to each sample. To verify this, let's examine this emotion dataset. Now, if we print the original emotion dataset train split and we verify the column names, so we have only the text and labels. But if we examine the same split from the emotions dataset encoded, we will have 2 extra columns added to this split and to the others. And these new fields, like input IDs and attention masks, are what is required by the transformers model. So just to recap, these fields are the model's actual inputs. So no raw text goes into a transformer model, just numbers. So after tokenization, each example now in the dataset will contain 2 extra columns, the input IDs, which include the token ID sequence, and the attention masks, which tells the model which tokens are actual input with value equal 1 and which tokens are padded to fix. Now data is ready. Let's talk about building our classification. DistilBERT model is trained for masked language modeling and not classification by default. That means that it was not originally built to classify emotions. So we need to add a classification head. So we have only 2 choices. The first, we extract the features, which means that we freeze the base model and train a classifier on top of them. Or we go to fine-tuning, which means we train the entire model. You will also hear the terms like BEFT, parameter efficient fine-tuning, LoRa, which is low rank, and other fine-tuning methods like BitFET and adapter fusion. We are not using those here. They are worth exploring when optimizing larger models. So we'll start loading the base DistilBERT model using the auto model class. That gives us access to the model's raw hidden state and not the prediction. So to break this down, we use the torch.device to assign GPU or CPU. Then we load the DistilBERT base uncased using the auto model class. And finally, we move the model to the selected device to our CUDA into our environment using the 2 device name. And it tells us that we have CUDA available, which means we have a GPU. So this will speed up the training. If not, the training still works on CPU, but just a bit slower according to your data. Great. Now let's warm up by retrieving the last hidden state from the DistilBERT for a single input text. To do this, we must convert our raw input text into a PyTorch compatible tensors using the tokenizer. So if we print the original text and we print its tokenization, this is what we have seen before. So this is our sample. This tutorial will show you how Hugging Face models can be fine-tuned using transformers, and these are the input tokens along with their attention masks. Okay, now we will call the tokenizer on this text and convert the results into PyTorch tensors, and we will get the results into encoded text PyTorch. To print the input size, then we print the encoded text PyTorch input IDs and its size, and it tells me that we have 1 row with 23 tokens, and we print the tokenizer output. So we can see that these are the input IDs followed by the attention mask. Now we can see that our input is in the format expected by PyTorch models, a dictionary of PyTorch tensors. Now let's define a function called getHiddenState. It takes a batch, and then for each tokenizer model input names, I will get their key and value from these batch items, and these are the key and values are the model input IDs and their attention masks, and I will call these inputs. Now I will disable the gradients, so there are no training at this phase, so I can do so with torch no grade, and then I will call the model passing the inputs, which are the input IDs and the attention mask, and get the output's last hidden state into our last hidden state, and return this to the CPU as a NumPy array. We will print DistilBERT hidden state on our example text, and I will pass the encoded text as PyTorch, the one that we have just seen here before, and return the results. So let's run this. So as we can see, this is the hidden state or the output array of the DistilBERT for our example here. Remember, as we described in the previous video, that we did that only for the first token. This is a regular or common practice in classification because this token already pays attention to all other tokens in our text. So extracting the embeddings for the first token or the classification token is commonly used to represent the entire sequence in classification applications. The reason is that this embedding consigns attention to all other tokens in that sequence. So the last hidden state or these numbers contains a dimension of the batch size, and in our case here it's only one sample, along with the sequence length and the embedding dimensions. So the batch size is the number of inputs in this batch, the sequence length is the number of tokens per input, and the embedding dimensions, which is typically 768 for DistilBERT model. Remember that with Torch no grad, it disables the gradient calculations, so we are not training the model. Now let's apply this to the whole data. So now we will compute the hidden state for the entire dataset using the map function. So I will call motion dataset encoded, and I will set format to torch, and only for the input IDs, attention mask, and so we transformed the format, and then let's check only the first row. So we are printing the emotions dataset encoded train split, the text column, and the first row, and its label, and input IDs, and the attention mask for the first row. Here is the first row. So I did not feel humiliated, and the label is 0, and these are the input IDs, and these zeros tokens are the batted tokens in this sequence, and these are the attention mask, and you can see that all batted tokens has an attention mask with equal to 0. Now let's call the map function on the emotion dataset encoded and pass the get hidden state function, which is this function that we have just viewed, that takes input as batch and return the hidden state after passing it to the model. And this will take long time if you are using a CPU. Now let's see how that is fast and quick using GPUs. Now let's run this cell. As you can see, it started mapping on the training set or the training split, followed by the validation and tests. And now we can see that every split in our training set now has an extra column called the hidden state of dimension 760. Now let's check the first example again, but we will add the hidden state. So this cell is exactly the same previous cell, but we added this extra line that prints the hidden state for the first row in the training split. Let's run it. And you can see here the output. First is the column names, and then the text, followed by the label, the input IDs, the attention mask, and now the hidden state vector for this sequence. So these 768 values are the output of the hidden state of the DistilBERT model for only the first row. But remember that we applied this to the whole data. Now let's create a feature matrix for classification. To do so, it's like traditional machine learning. So I will define emotion X train to be a NumPy array that includes only the hidden state, and the emotion X validation, which will contain the hidden state for the validation split, and the emotion Y train, which is a NumPy array for the labels for the train split, and the emotion Y validation, which is the label for the validation split. And let's print these shapes. As we can see here that the training set shape has 16,000 rows. Each row is 768 value or columns, and these are the output of the DistilBERTs. As you can see here, We don't have text. We only have numbers, which are the hidden state that the model DistilBERT has generated. Let's run the cell. Now we'll use a traditional logistic regression for classification and train it on this dataset. So we'll import the logistic regression class from the scikit-learn linear model library, and we will define an instance of it called logistic regression. We will call this model as our logistic regression classifier. We will train it on the X train, and the Y train are simply the hidden state for the training dataset and their labels. And let's print the score for this model on the validation dataset. So it takes a few times to train the model. So logistic regression gives us a score of 0.6335 accuracy. Now, this simple model gives us like a strong baseline using only DistilBERT embeddings and with no fine tuning, which means that we did not fine tune the DistilBERT model. We just trained the logistic regression on the output of the DistilBERT hidden state. Now let's compare our logistic regression model with a baseline or a dummy classifier that only predicts the most frequent class. To do so, we imported the dummy classifier class from the scikit-learn. The dummy initiated an instance with the strategy most frequent, and we called it the dummy classifier, and we trained it on our emotion X train dataset and its labels emotion Y train. And again, we will print the score for this dataset. As we can see, it's simple, it's quicker, and it only gets us a score of 0.352. Let's move on to option 2, where instead of building a classifier manually, Hugging Face gives us a shortcut like auto model for sequence classification that enables us to fine-tune the entire DistilBERT model end-to-end for classification, which means that it gives us the DistilBERT model with an extra classification head on it. So what is the benefits of fine-tuning? Fine-tuning allows the model to adapt its internal weights to the target task, improve the performance on a domain-specific data, potentially surpass the performance of frozen features approaches as we have seen. So let's load now DistilBERT as a pre-trained model, but for classification. And this can be done by using the auto model for sequence classification class instead of just auto model. And now we will have the DistilBERT backbone as a pre-trained model and a classification head on top of it. But we need to specify the number of output labels. And in our case, this is 6. So the auto model for sequence classification class wraps the base model for DistilBERT with a trainable classification layer. And this is ideal for supervised tasks like sentiment analysis, spam detection, and in our case, emotion classification. So to do so, we import auto model for sequence classification from transformers, and we imported the accuracy score and the F1 score, and we defined a variable called number of labels equals 6, and then we call the auto model for sequence classification class from pre-trained. We are using the same checkpoint and passing the argument number of labels to 6 and into our device, which is the CUDA device, and we will call this the transformer classifier. Now let's run this cell. It loaded the model. You might see a warning that some model weights were randomly initialized, and this is normally because the extra classifier layer that is added to the DistilBERT backbone to the DistilBERT pre-trained model as a backbone is initialized randomly. Now, to evaluate our classifier, we will use accuracy, precision, recall, and F1 score metrics. And it's not enough just to train a model. We need to measure how well our model performs. So we'll use these 4 metrics: accuracy, which is how often the prediction is right; precision, which means how precise are our positive predictions; recall, how many true positives we catch; and the F1 score, which is the harmonic mean between the precision and recall. So we'll define the helper function that is called compute matrix that takes a patch, gets the argument maximum for the index with the maximum value from the predictions and get the label IDs for this batch, and then it passes both the labels and the predictions to the accuracy score, and both the accuracy and F1 score as a result. So why do we need this function? This function will be passed to the Hugging Face trainer class. We'll just talk about it in a second. So to break it down, it takes the prediction labels IDs, which are the true labels, and the predictions to argument max with -1, which are the predicted labels, and we calculate the precision, recall, F1 score, or accuracy, and return this back. All right, now we have processed the dataset, we defined our model, and set up our evaluation metrics. It's time to fine-tune the model or fine-tune the classifier. So let's configure our training loop using the Hugging Face trainer class or trainer API. So trainer class or trainer API is a high-level class that abstracts away much of the boilerplate code for training and evaluation. It manages training loop, it manages evaluation, logging, checkpointing, and pushing the models back to the hub. We will use another class called the training arguments to configure the behavior of the training process, like the batch size, learning rate, number, etc. Let's see this in action. But first, let's log in into Hugging Face. So here, it will ask you for a token ID or security token from Hugging Face, and you can get it from your account. And I will get it just right away. You can get these access tokens from your account. And you can just copy it and just paste. So to push our fine-tuned model to our Hugging Face account, we need to authenticate. So as I said, we will use the training arguments class to control the process, which means I need to define what's the number of epochs, batch size, checkpoints, etc. This is the fun part. We define everything from learning rate to how often to save the checkpoints. Let's write our training configuration. So Hugging Face makes it really easy to manage training. So we just use training arguments class and we define in it a lot of controls. So I define the batch size to be 64. Feel free to change this to 128 to 156, and the logging steps to be the 16,000 rows of the train split divided by the batch size. So every batch size I need you to log it, and the model name to be the same model checkpoint, which is DistilBERT uncased, along with fine-tuned. So we understand that this model is a fine-tuned version, and on the emotion dataset. And this is the name that we will see on our Hugging Face hub after fine-tuning this model. Then we initiated an instance of the training argument class with output directory, which defines where is the folder that we will save this model after fine-tuning in, and the number of training epochs, the BERT device training batch size, and the evaluation batch size to be the same size, the learning rate, weight decay, evaluation strategy to be per epoch, and enable the progress bar, the logging steps, and pushing hub equal true if we need to push this into our Hugging Face hub account. Now all what we need now is to instantiate the trainer class. To instantiate the trainer class, I give it the model to be our transformer classifier, which is the DistilBERT downloaded from the auto model for classification class, and we pass the training arguments. We pass our evaluation metrics function, which is the computer matrix, and the training dataset to be the train split from the emotion dataset encoded, and the evaluation dataset will be the validation split, and along with our tokenizer. So now we instantiate the trainer class, and we call it the trainer. And we pass our transformer classifier, which is DistilBERT from the auto model for classification class, along with these training arguments and our evaluation function, along with the train split as the train dataset and the validation split as the evaluation dataset and our tokenizer. Then we simply call the trainer.train. Now let's So the trainer class will tie everything all together, and it will handle batching, backpropagation, optimizer, logging, all under the hood. Let's run this cell. Okay, now it will ask us API key from the bias website. So we keep logging. So you can click on this link. It will ask you to log in. And then just copy and paste this token into the cell that it asks. And press enter. Now, after everything is ready and we run this line, the training began. And we saw how the progress bar logs losses and metrics printed for each epoch here. And we can see here that the accuracy and the F1 score is much better than our traditional logistic regression. So it looks like this model accuracy is much higher. So to wrap up this option again, so we fine-tuned the entire DistilBERT model instead of using it as a frozen feature extractor. This means that updating all the model weights, and it's not just the classifier layer. It's more powerful, but also requires more data and compute. But it fine-tunes this model on your dataset on hand. So why do we need again a classification head? Because the model's base outputs are just token embeddings and they are not predictions. So we need a trainable output layer to map them into our emotion classes. Fine-tuning helps the model to learn from your task-specific data. It adapts the emotion classification task and it improves beyond frozen feature approaches. And especially when your dataset is small, this technique will help you to get more from your pre-trained knowledge. So instead of using the auto model class, we use the auto model for classification, which includes the pre-trained DistilBERT backbone and the trainable classification head. Then we find the number of classes to be 6, and this is exactly the number of emotions that we have in our dataset. And the weights for the extra classification layer or the extra classification head are randomly initialized, so we will train them from scratch. And that's why it gives us the warning that some of the weights of the DistilBERT were not initialized from the model checkpoint. Then after that, we defined our compute matrix to monitor how our model performs during the training. It takes in the predictions and labels and returns the accuracy and F1 score for trainer late. And this function will get passed later to the trainer class. So it extracted the predict class labels using the argmax and compared them to the actual labels and compute two things, the accuracy and the F1 score. Then we logged into our Hugging Face hub. And then we defined the trainer class, which is the power behind the training in Hugging Face. It handles the training. It handles the training and evaluation loops, the logging, progress tracking, saving checkpoints, and pushing the models to the hub. So it makes our life with training much easier and no manual PyTorch boiler. At the end, we call the train function from the trainer class. And before using the trainer class, we used the trainer argument class from the Hugging Face to define how training should be done. And we defined the output directory, and we defined the training number of epochs, and we will log into the weights and biases W and P to track the metrics live during the training. So before we dive deeper in the future with fine-tuning, we will have a couple of short dedicated tutorials to explore and explain prompt engineering and template-based fine-tuning. So in these upcoming lessons, we will explain how prompting works with language models and how they are used during training. So let's stay tuned for that lessons next. So now let's run this trainer to predict the validation split and get its predictions, and then we print its matrix. So if we run this, we can see that even on the validation, we have an accuracy of 0.92. So the predictions, so we can see that the results includes also the raw logits, which means the model's confidence score for each class. Let's see NP argument max to convert these into a predicted class. So I will print the model predictions, get me predictions.shape. It gives me the validation split has 2000 rows with 6 values for each row. If we print the predictions at the first row, it will return the 6 logits values for these predictions. And if I need to get the predictions with argument max, it tells me that for this row at index 0, which means this is a class 0. So we are not done yet. It's time to dive into error analysis. And by calculating bare sample loss, we can find which samples the model got wrong, how confident it was, and what patterns it struggles with. This is a good practice to implement and enhance your model. And sometimes you might need some pre-processing to increase or boost up the model's performance. So we defined a get model output loss that. So this function does something really powerful. It calculates the individual loss for each validation example, extracts the predicted labels, and adds new columns to the dataset, the loss and the predicted label. Now all we need is that to sort the data by loss and investigate the high error samples. Here we defined a helper function called label integer to string that takes the numeric label IDs to human readable class names like joy, fear, and anger instead of just the label's indexes from 0 to 5. So this, and then we set the format of the emotion dataset encoded back to pandas, and we define the column names, especially for the last 2 columns added to be the predicted labels and loss. Then we define a validation data frame to be the emotional dataset encoded for the validation split, all the rows for the 4 columns. Then we apply the helper function to map the label ID into its name and call this column a label. And then we define another column called the predicted label. So now we have the label name instead of the label index, and the predicted label name instead of the predicted label index. And then we sort this data frame and we print the first 10 rows. So let's run this cell. So here we have the top 10 classified examples from the validation set sorted by the highest loss values. These entries reveal where the model struggled most in aligning predicted labels with ground truth. This helps in identifying patterns of confusion and potential areas of dataset improvement or model architecture adjustment. So before we continue, you can notice here the folder that has the model that has been fine-tuned along with all its files, weights, and tokenizers. And you can see the name that we have defined at the output directory to be DistilBERT base uncased fine-tuned emotion. So now that the training is done, we can save and upload our fine-tuned model to the Hugging Face Hub under our account. We can use this using the trainer to push to Hub, and we can add any commit message during that. So with that single line, we can push our entire model, weights, configuration, tokenizer, and metrics to the Hugging Face account under our account. So let's run it. So now you can use this model or embed it into your applications. And you can use it just as simple as any other model that you have used in the past with pipeline interface. So to do so, we import the pipeline API from transformers, and we define the model checkpoint to be your Hugging Face account along with the fine-tuned model name that we have defined. And we call the pipeline API with the text classification and the model checkpoint that we have, and you call it as a classifier. And let's try this on a sample. And this is a tweet that says, I am really happy. I know how to do fine tuning with Hugging Face. We pass this tweet to the API, to the pipeline API classifier. and we get the predictions and print it. So let's run this cell. And as you can see, it has a score of 0.97 for the label of 1. And now we have successfully deployed our custom model onto our Hugging Face Hub account. So anyone can just use it just like this. So let's recap what we have accomplished in this hands-on tutorial. We explored the emotion dataset with the Hugging Face dataset library. We tokenized the text using a pre-trained DistilBERT tokenizer. We compared frozen BERT classifier versus full fine-tuning. We trained using Hugging Face Trainer API. We evaluated metrics like accuracy and F1 score. We performed error analysis on the worst predictions. And finally, we uploaded our model to Hugging Face Hub. So this project can be used as a blueprint for any text classification task, whether it is spam detection, topic classification, or emotion analysis. So if you found this tutorial helpful, please like and share the video. Subscribe to the channel for more AI and machine learning contents. Check the GitHub link in the description to grab the notebook and leave a comment. What would you like to fine-tune next? Before we go, here is what's coming up next on our channel. In the next video, we'll take everything you learned here and apply it in a real production environment on the cloud using AWS SageMaker. We will see how to fine-tune the models at scale, use managed training infrastructure, deploy our model with real-time endpoints. Plus, we are also preparing a focused tutorial on prompt engineering and explore techniques to guide and control language models without retraining. There is a lot more coming, so stay tuned. At the end, if you found this tutorial helpful, please like and share this video. Subscribe to the channel for more AI and machine learning contents. Check the GitHub account link in the description below to grab the notebook and leave a comment. What would you like to fine-tune next? Thanks for watching. See you in our next tutorial. Have a good day.